So Earth Genome, that's the place that we work. We are a nonprofit. If you haven't heard of us, we're relatively small, but we operate as a tech startup. And so we're pretty lean. We're about a dozen people, depending on which day of the week that we're on. But we try to have a global impact. Some of the projects that we work on, some things like Climate Trace, which is an Al Gore initiative to track methane emissions around the whole world independently. We also do a lot of watch applications to see how things change in environmental modeling over time. And specifically, we're going to talk about Earth Index and dive a little deeper into that. So what is Earth Index then? That is a tool that we've built with the goal of finding anything anywhere in less than a day. The less than a day is the important bit, and I'll kind of start at the beginning. We'll go back a little bit. Before, we were doing what a lot of other people were doing, where if we wanted to find something, we would get a bunch of labels that we created and were very supervised, train a model to find that one specific thing, basically say, is it a hot dog, not a hot dog kind of thing, and then in this example with Global Plastics Watch, after months of effort, we'd be able to find things around the world. Then in 2022, foundation models started to emerge, geospatial foundation models specifically, and so what that allows us to do is not head towards training for one thing, but instead build on top of that foundation model to generate embeddings, and that's really comes out with a semantic meaning for imagery, and we're able to do fast things like geospatial search, change detection, and classification. Here's an example of that. So this is a visualization of the state of Alabama. You saw it start with kind of the spatial representation, and then it chunks around to group instead by vector embedding and similarity of those embeddings. So once you go into individual images, you can say that these things are more like these other things that have been embedded. All of that's really great, but how do you turn this into a thing that people can use? And that's where Earth Index, we've started to build that into a product that people can easily use in really a three-step process where you assign some labels. So we've gridded the entire world, and you can pick some chips and say, here's some chips that have the things that I want, and then click a button to run some predictions, and then within seconds, get back a lot of other representations that are more or less like the thing that you wanted to find. And you can iterate on top of that a little bit to say, maybe we have a false positive, and we want to get that out of there and make the results even better. I want to be clear that this isn't just something that we're like, oh, this would be neat if we did this. We are already doing this. So around the world, in different places, Climate Trace, we're tracking greenhouse gas emissions for cattle feedlots that weren't ever tracked before. For methane emissions, we're finding narco trafficking in Peru, illegal gold mining in the Amazon as well. So we are actually headed towards that real world impact for this tool. Something that made it a challenge before is that we were running these embedding pipelines to find things in specific AOIs. And so we had to talk with somebody and say, hey, what area are you interested in? And then we'd run all of our pipelines for that. About a month ago, we decided that we really needed to make global embeddings, and we've been working towards that. And so we released the global embedding set onto Source Co-op as well. And so now you can draw an AOI anywhere in the world for the thing that you want to find, and then 3.2 billion overlapping tiles and vectors. You can search through that now. If you're interested, scan the QR code, go to that website, take a picture, and you can sign up for the wait list. If you know other people, organizations, really the frontline defenders that are doing this kind of work that this tool would be useful for, let us know. We're letting people off of the wait list right now, getting that beta feedback and everything else, so we'd love to talk with you about any potential use cases, and come talk to us if we need to speed you along the wait list at all. Now, all of that sounded probably like a marketing pitch. I call it an impact pitch because we're a nonprofit, but we're at the Cloud Native Geospatial Conference, and so that's where the how we do it comes in. Before I pass it off to Quinn, I'm going to go very hand-wavy architecture on how we actually do this. We really have a processing tier and then an application tier. So the processing tier, you can split it into two parts. One where we need an imagery pipeline. So we have to find a bunch of imagery, specifically cloud-free imagery. So we're doing a bunch of searching to generate that mosaic data set first, And then once we have the data set of clean imagery, we have to generate all of the embeddings, and that's a completely separate pipeline that we run some models from the Zoo Lab and generate that and push that out as well into GeoParquet. Finally, we move on to the application tier. So once we have all those bits and pieces, we have to make it fast. And so we have really, really big databases in clusters around the world to spatially break things up and make stuff fast. And then we put an application on the front end on top of that to make it usable. To call out some of the specific cloud native bits in there, we've got some Stack, we've got some COGS, Source Co-op, Parquet, and I'll pass it over to Kwin now to dive a little bit deeper.
Thanks, Brad. Hey, everyone. We're going to dive into the weeds just a little bit here. Not as much as I would like, but I hope it's instructive. So the first thing that we're going to talk about is the imagery pipeline. Earth Index is about making Earth observation data searchable. And in our case, we're doing searches on Sentinel-2. Sentinel-2 is great for us because it's multispectral, so we have multiple bands that we can take advantage of. It captures the globe every 5 days. That's important for us because Earth Index is a global tool. And sort of a logistical note, all the Sentinel-2 scenes that we use for our mosaics and ultimately our embeddings are sort of transposed onto the MGRS grid system. And then lastly, like Brad said, we really need our imagery to be cloud-free. So that means we're having to mosaic images together. And we choose to do that on an annual basis. You could do sub-annual. We hope to get there eventually. But for now, it's just these annual mosaics. So the biggest challenge in creating all of these cloud-free mosaics is how to pick the right scenes. As you know, Sentinel-2 has, it's imaging the Earth, so any clouds, any snow or ice that ends up in those scenes is sort of a barrier to finding things. On an annual basis, you could be looking at over 1 million candidate scenes to build your mosaic for that year. So our most powerful tool in choosing the right scenes is actually Earth Search, which is built by the wonderful folks at Element 84, along with AWS. For my money, the best part about Earth Search is its Stack API. It makes sifting through those millions of images a lot easier. You can search by location and time, and then you can order those results by percentage cloud cover. Pick the scenes that have the least clouds in them. And I'd say it almost goes without saying in 2025, but Earth Search's assets are stored in a public S3 bucket as COGS, which is great. So the first time we built these annual mosaics, this is what it looked like. I mean, when I first saw this, I thought, hey, that looks pretty cool. That is the Earth. The green bits are green. The desert, it looks like desert. But there's also some problems with it that I'm sure you can see. The second time we did this, this is what it looked like. And this is 2023, by the way. So much better. How did we do that? We took advantage of Sentinel-2's scene classification attributes, which Earth Search makes available as Stack attributes, which is really nifty. So you can figure out, without even opening up the scene classification layer, is this a cloudy image? Is it a snowy one? You can find that out really quickly. So we took care of some things, missing pixels. I mean, that's really bad, but we made it better. Snow and ice again, and getting rid of those nasty clouds. This is from a part of the Amazon, which is really cloudy all year long. And the partners we work with, a lot of them are working in the Amazon, so getting rid of those clouds is important. Another big challenge of creating these annual mosaics of this imagery is the cost. It's a lot of data, and so one of the best tools that we found, this is not sexy or groundbreaking or pioneering, but just choosing the right compute architectures. So in AWS, ARM chips are generally about 20% cheaper than if you were to use the same compute resources that on a x86 architecture. Part of that's because they use less energy. Fewer kilowatt hours equals fewer emissions, which is great. So once we have all of our cloud-free imagery mosaics, we can generate embeddings. We use a particular foundation model, but really this field is advancing all the time. It seems like there's a new geospatial foundation model coming out every week. Sort of the high level here is that we take our imagery mosaics, AWS batch, one job per MGRS grid cell, and out comes a big old GeoParquet file. It's not really that big. It's maybe 400 to 500 megabytes, I'd say. But inside of it are about 200,000 vector embeddings. And like Brad said, we make those publicly available on Source Co-op. We think that there's value in sharing data openly, even when you're not entirely sure how it's going to be used. We want to see what people do with it. This is what one of these GeoParquet files looks like. As you can see in the middle column there, you have your 384-dimensional vector. I guess that's where the magic happens. Again, biggest challenge with the embeddings pipeline is minimizing the cost. And one of the best ways we found to minimize the cost of generating them is just to be patient. AWS batch has spot pricing that rewards you if you can be patient enough to wait for sort of lulls in computing demand when it's cheaper. And it's also great because if your workload can tolerate interrupts, great. I don't care if it didn't complete this time, I'm just going to retry it again. So once we have all of our embeddings, we make those embeddings searchable by using just a sort of traditional database. We take those 3.2 billion vectors from 1 year and just put them right into Postgres. Nothing pioneering about that, pretty boring actually, but it works for us. Our database is sharded and partitioned spatially, and we've got both in-memory indexes for our geospatial queries as well as vector indexes that allow you to do your nearest neighbor searches on those embeddings. This is just what the database shards and partitions look like. We have three big shards. They're just EC2 instances. Nothing special about that. So this is, I've mentioned cost a lot. That's really important to us to make this affordable. We're a very small company or a nonprofit trying to make a big impact. So what we found works really well to reduce the cost is just to do it yourself. Cloud vector databases are shockingly expensive. So we kind of went a different route where we just stuck to the good old tools like EC2. So actually yesterday, this is maybe the worst case example, but I was looking at one of these cloud vector database providers, and our 9 terabytes of embeddings would cost $3 million a month. I'm sure they would give us a discount, but that's quite a few zeros that we would need them to take off, and I don't think they want to do it. So our setup for the database costs about $9,000 a month, which is pretty great. Brad.
Thanks, Quinn. Just to round us out here, thank you to all of our supporters. Again, we're a nonprofit, so we work with some great foundations, great partners in the industry. Potentially work with you if you are interested. Come talk with us. If you have a bunch of cloud compute credits sitting around, I'd love to talk with you. Also, a thank you to Jed and the whole team there at Radiant Earth and Source Co-op. We love that we have been a part of that community, and we love to be here today contributing. So again, I'm Brad, this is Quinn. We're at the Earth Genome. Any questions?
Thanks for sharing. It's okay, I can talk loud. Thanks for sharing. This was a super exciting presentation. If I can, I have 2 questions. My first one is when users come and they're finding things they care about, like deforestation, what time span are they working on? Are they working with like the previous year's Sentinel? Can they go back at each annual step? Have you processed? Or can they do something with like monthly composites?
Yeah, that's a great question. Right now, it's yearly. So we do a yearly composite. We plan to run multiple years as kind of a first pass. And then we've also talked about either quarterly or monthly or those different time ranges, because that would allow people to do that change detection a bit more. Yeah, to understand that.
Yeah, I'm sure it's super costly, but something like quarterly would be very compelling. And one more, if I may. You said there's like one foundation model you've used to train your embeddings, and that like new foundation models are coming all the time. How do you approach like iterating with those new models in like smaller areas, if that's something you all are thinking about right now?
Yeah, that's something we're thinking about often. We work with a great group, even though we're a small group. Dr. Ben Strong is on our team, and he does a lot of the evaluation of those models. Again, with also Ed Boyda is also on our team, and they routinely run benchmarks and are trying new things, particularly in smaller areas. What you've kind of seen here with Earth Index is more the product polished bits. Behind the scenes, there's a lot of that actually seeing what works, running our own benchmarks. We're looking to the industry to see those benchmarks develop more so we can actually understand better where that baseline is, because we decided specifically not to build our own foundation model and to build on top of that, because that's the way we can make a bigger impact. We're about time. Yep.
I have a question, 2 questions. I think the first one you kind of answered, which was the annual mosaics, because I was going to ask like what happens if there are interannual events, specifically if there are stochastic events like forest fire where there's a recovery and you're basically mosaicing something that is burned and something that's half burned. What happens then? So I don't know if you still have thoughts on those pieces. And the second question, I can wait for the first time.
Yeah, the first question, that is really tricky. So our mosaics are actually, of all the pixels that we use out of the scenes we've selected, we take, it's like the first quartile of all those scenes. So it's not perfect. We've also played around with using the median, but essentially, like if you had, we end up using 5 to like 25 scenes. Any event like that is going to be kind of, sort of mixed in with the other scenes from that. But it is a hard problem, and that's sort of one reason to go to subannual to have greater clarity. I think we have one more time or a question.
Yeah, and this one is going to be small, but right now it says if something looks like something, but that's something that a user is picking right now is a pre-embedded chip. A user cannot upload their own image where you are going to do the embedding on the fly and then search across your vector database, right? Right, yeah.
The user would use the Earth Index web application. You could also probably do this in a Jupyter notebook. But yeah, you're going to be using the imagery that we've curated and selecting individual chips as your positive labels.
I will add, that's something that's been on our mind in our longer-term roadmap. With roughly a dozen people, our roadmap is a little bit long, but if that's a use case that you think would be useful to a specific group, I'd love to talk about that more.
Great presentation, really excited about your work, really, really inspiring. I have 2 questions. One is, so X-ray and ZAR could be abused to be a serverless vector database. I think this is like under-documented, but all the pieces are there. What are the performance characteristics that you would need for your real-world system in order to try to adopt serverless technology to build like a vector store index that's, let's say, potentially radically cheaper?
I mean, like just simply put, a user who's not a technical person needs to be able to have their search complete, I don't know, certainly within a minute, ideally less than 10 seconds. Yeah, the project areas that you can define in Earth Index can be up to 900,000 square kilometers. So that's still quite a few embeddings that you're going to have to search over. So yeah, if ZAR and Xarray can have that search query complete quickly, great. We would love to see that.
And the follow-up question is, large language models, or like, the World Foundation models, are getting bigger and bigger context windows. How do you think you might see yourself adapting to like less dependent on traditional RAG systems or embedding databases? Probably in geo, you'd always need to have a traditional search index all the way to like a, inference engine or lookup. But how might you balance those things as you see that technology trend evolved?
Brad, do you have any thoughts?
I would say that we're always forward-looking on as things evolve. Something that comes to mind is exhaustive search. So what we've shown is really just finding like a nearest neighbor search through these embeddings. That has a certain limit. And so what can we do after that? So after that first pass, do we queue out a job and let that run and do additional processing to get even better? We're currently experimenting with that, and that's on our nearer term roadmap. But right now, it's still a little bit away. Yeah.
Thank you so much.
Thank you all very much.